Hello students, welcome back to our course Environmental Modeling and Simulation. In today's lecture, we will continue our discussion of the paper that we were discussing in the last lecture to understand the application of empirical approach. We have been investigating this particular paper titled A Model to Investigate the Impact of Farm Practice on Antimicrobial Resistance in UK Dairy Farms. And this is a recent paper that used the empirical approach. And if you, as a reminder, empirical approach is when you build the model using mathematical dynamic equations. And in this case, they use ordinary differential equations, which are also the most commonly used empirical approach. And we spent last two lectures building the model, trying to understand what these authors of this paper did, why they did. Let's remind ourselves that we are looking at the slurry tanks in UK dairy farms. They have a seasonal fill and draw cycle. So there is a seasonal emptying that's done in United Kingdom for the slurry tanks. The slurry tanks receive antibiotics, and as we discussed in the previous lectures, the antibiotics can be broadly classified into two kinds of antibiotics, the bacteriostatic and the bacteriolytic. We spent plenty of time discussing how the exposure to these two different kinds of antibiotics can be deadly for bacteria, especially the target bacteria, when the concentration is above a threshold value. And when it is below that threshold value, the same antibiotic can trigger the selection of an increase in the ability of microbes to resist antibiotic therapy, which is referred to as antimicrobial resistance in this paper. Now, the slurry tank receives not just the dairy slurry, but also the wash water, the wastewater, and the antibiotics used in the farm. So, we developed a model in the previous two lectures which incorporated both different kinds of antibiotics, different kinds of bacteria, and we said that broadly we can say that we have total bacteria, we have sensitive bacteria, we have bacteria that are resistant to antibiotics that are bacteriolytic, resistant to bacteriostatic antibiotics, and multi-drug resistance. So, population that has resistance to both bacteriolytic and bacteriostatic antibiotics. And we are very interested in seeing how the population of these different kinds of bacteria, the sensitive ones that are sensitive to antibiotic resistance, antibiotic therapy, not resistance, ones that are resistant to bacteriolytic antibiotics, bacteriostatic antibiotics, and ones that are resistant to both bacteriolytic and bacteriostatic antibiotics. We made numerous assumptions in this model. The authors made numerous assumptions that we discussed. And remember, as I mentioned just now, that this particular slurry tank has seasonal emptying. So, depending upon the seasons, it is emptied. It also receives rainwater. It is open to the atmosphere. And once it is seasonally emptied, we also want to understand human activities like emptying the slurry tank, if it has any effect on the levels of these resistant bacteria in the slurry tank. After developing this model, the authors of this paper simulated the model, and in this course we have 4 lectures where I teach you how to use MATLAB and R to simulate simple models like the ones we have covered in this course. Now, this model is slightly bigger. Its simulation on MATLAB or R will be slightly more difficult than the examples I have given you in this course, but at this stage for this course, knowing how to use MATLAB for simple models is sufficient. Okay. So, once they had simulated, they got data regarding how the concentration of sensitive bacteria, which is susceptible bacterial population denoted here by blue dots, bacteriostatic resistant bacteria denoted by orange dashes, bacteriolytic resistant bacteria denoted here by ochre dashes, and multi-drug resistant bacteria denoted here by purple line. So, this is bacteria that is resistant to both bacteriostatic antibiotic and bacteria that is resistant to bacteriolytic antibiotic. And the MATLAB or R, both of them will give you a table like this, which will have a column for time. So, as time changes, how is the susceptible population changing, how is the bacteriostatic resistant bacteria changing, and then bacteriolytic resistant bacteria, and then MDR multi-drug resistant bacteria changing over time. So you will get this matrix, this table from both R and MATLAB. Using this information, you can plot using any plot device. MATLAB has an inherent plotter, and we have looked at it in this course, and we will look at it further in our MATLAB related lectures. R also is a very powerful plotting platform, and it has a very nice package called ggplot2, which I highly recommend you to explore, but it's not part of this course, so we're not going to dwell on it. But once you get a matrix like this, you can plot and make beautiful diagrams like the ones I'm going to show you. This lecture today, since we have already developed the model, we have already discussed the model. In today's lecture, I want to spend time going through the kinds of results that you can get using empirical approach. Now, a big question that we have is empirical approach is not always informed completely by the real life observations, which is partly true, because the parameters that we put in our empirical model do require input from real observations. So empirical approach, even though it is something that we do on computer, something we do in silico or on paper, does utilize information from real world. So it is not out of touch of reality, it is informed by the observations. It also requires an extremely good understanding of the phenomena, without which we can't generate models that are reliable. So and once you have generated the empirical model, you can vary the scenarios. For example, we'll see very soon how in this paper they vary different scenarios and try to understand what if we change the kind of antibiotic, what if we change the emptying frequency, how will it impact the levels of antibiotic resistant bacteria, multi-drug resistant bacteria in the slurry tank, and how we can modify or what interventions we can do to minimize the environmental problem. So in this diagram we see that the susceptible bacteria die out pretty quickly in number of years. So x-axis is in years. So if we are planning to have a slurry tank, a dairy farm in a place in UK for 10 years or so, we should know that only for first few months the susceptible bacteria will be a significant portion of the total population, and very quickly the bacteriolytic resistant bacteria will take over, which is the ochre dashed line. And over time, like definitely after a few years have passed, the multi-drug resistant bacteria, their numbers will increase. So this is the data that we get using the information we have from the farm as parameters in our model. Now here, once you have a working model on your simulation platform, whether it's MATLAB, R, Mathematica, Octave or whatever, you can vary things. So what happens when they said that the rate of MDR transfer is 0? We have drugs, we have chemicals that we know can stop the transfer of can stop the horizontal transfer of antibiotic resistant genes. So if there is a way to stop the transfer of multi-drug resistance, which is to set beta U from the previous lecture to 0, how will that impact the total number of bacteria which are susceptible or resistant to either of the antibiotics? So if you are able to stop the transfer of multi-drug resistance, so just set the beta 0, this is the result that we get. Now this is very important information, because as environmental scientists, environmental engineers, we can offer it to our regulators and to our dairy farmers, or in case of wastewater treatment plant people, that hey, if we add this particular compound, we might be able to set this parameter 0, which will reduce the total number of multi-drug resistant bacteria. Okay, again you can set another parameter to 0. So we are trying to look at what interventions will have what extent of impact. If you remember, we did something similar when we looked at the epidemic model. What will happen if we reduce the interaction between the sick and healthy people, right? Or what happens if we reduce the transmission rate between sick and healthy people, which is where the social isolation, the physical isolation, and using mask, keeping the distance come into picture in case of epidemics. So here we are trying to set the cost of multi-drug resistant for bacteria to a particular value, and then we see how it is going to vary. Now similarly, let us look at the impact of seasonal emptying regime. As I mentioned, this particular slurry tank undergoes seasonal emptying. In upcoming lectures, we will be looking at different kinds of reactors in detail, like batch reactors, CSTR, PFR, and the reactors that undergo seasonal fill and draw cycles, not seasonal, sorry, that go fill and draw cycles, and we will learn how to model them. Now, just to be clear, modeling these reactors is not exactly empirical approach that we have studied so far, but again, it builds upon the basic logic that we have learned in this course. So, if we include seasonal emptying regime in this model, we notice how the levels of multi-drug resistant, bacteriolytic resistant bacteria, bacteriostatic resistant bacteria and susceptible bacteria change over time. Now, notice one thing, that to do this study and to estimate the changes in the levels of different kinds of bacteria over time and over the course of 10 years was much faster and more economically feasible for the researchers to do it in silico than to actually take these measurements or wait 10 years to get the real life measurement and verify the model. So, this I hope really helps you understand the importance of modeling using empirical approach. Just to clarify, we have data analyses and data fitting approach in modeling, and we have empirical approach in modeling. Now, empirical approach, if we really understand the phenomena well, if it is used nicely and it's also occasionally verified against real life observation, if the parameters are informed by real life observations, empirical approach can be fast, easy to do and can inform, which is also the approach of this paper. Data fitting and data analysis kind of modeling, where we fit models to the data that we already have, is something that in my lab we say it falls under the domain of statisticians, which is not very accurate, but this is when you have data. So, for example, if we had data from slurry tank for last 10 years and then we try to fit a model to it to understand how things are behaving, then this could have informed our empirical approach to modeling antibiotic resistance in slurry tank from dairy farms. However, this particular model, as we looked at in the previous two lectures, is already informed by wealth of literature from multiple studies. Okay, so let's look at some of the results, what observations the authors made and how this could be beneficial. So, here is when we do not empty, when we do not undergo seasonal emptying, and when we undergo seasonal emptying, how the antibiotic concentration changes. If you remember, we not only looked at susceptible bacteria, bacteria resistant to BL, which is bacteriolytic antibiotics, bacteriostatic antibiotics and multi-drug resistance, but we also looked at the concentration of bacteriolytic antibiotic, bacteriostatic antibiotic. We also modeled that, assuming first order decay for both of them, and remember we looked at fill and draw cycle. So, if there is no seasonal emptying, then we notice that the model says that very quickly the concentration of antibiotics will go down. However, if we undergo seasonal emptying and drawing, concentration of antibiotics, total antibiotic will fluctuate with seasonal emptying and drawing. So, even though this has not been experimented, the model is telling us that when we change the seasonal emptying regime of the slurry tank, the antibiotic concentration varies. So, if we do not empty at all, then it goes down. If we are doing seasonal emptying, then it fluctuates. So, we know that no emptying seems to be better for controlling antibiotic concentration than seasonal emptying. So, now we can play around, because this is in silico, we can play around with changing the frequency of emptying the slurry tank. So, here it's we have on x axis inter-emptying interval. So, basically after 5 days, 100 days, 50 days, after how many days are we emptying the slurry tank, and how much time it is going to take for multi-drug resistance to develop on y axis. And in B, we are changing the tank volume. If you remember, tank volume, because it is a fill draw cycle, tank volume is very important. Now, you may say, well, tank volume is constant, but the effective volume of the reactor changes with fill and draw cycle. This is very important plot. It is a result of an analysis that I am going to demonstrate towards the end of the course, which is known as sensitivity analysis. So, sensitivity analysis is basically when we have a model and we have some parameters that have been informed by real life observations. So, for example, let us say we have logistic growth model, right, very simple. We need two parameters here, one is the growth rate and one is the carrying capacity. Now, let us say for the particular kind of organism that I am studying, and let us call it organism A, and the organism A, let us say it belongs to a particular class of organisms. The class of organism is known as class alpha. So, let us say in other studies we noticed that a related organism which is not A, but let us call it A2, belonging to class alpha had a particular growth rate R dash and a particular carrying capacity K dash in the given experimental settings. So, when I am doing the modeling for the growth rate of this organism A, which is a distant relative of A2 or close relative of A2, belongs to the same class alpha, and I am using the same model, my setting in my experimental settings might be quite close to what this study had. So, my experimental setting is comparable, but not exactly same, and the bacteria or the organism I am looking at is also comparable, but again not exactly the same. Now, how do I estimate R and K values? What I will do is I will look at relevant studies which looked at similar bacteria like A3, A4 all belonging to class alpha. I will look how the R varied. I will look into the literature how K varied among these different studies, because my particular situation is not exactly the situation of other people, even if it was of other studies, even if it was the exact experimental setting, but with time things might have changed. So, I can look into the literature for the range of the values, like R varies from let us say 0.2 to 0.8, K varies let us say from 100 to 1000, and once I have that range I can input a value of R in this range that makes sense to me for my given settings. So, let us say for this particular bacteria or organism A, which has not been studied in the exact setting before, I choose R is equal to 0.4 and I choose K is equal to 200, okay, in the range that we have looked into the literature. Now, this is not exactly the number that exists in my setting, in my experimental setting, or the target area, the focus site that I am looking at. So, let us say I have an error rate here of epsilon R, error rate here of epsilon K. This error might completely change the results that I see or the predictions that I make using my model. It is very important to understand what is the extent, what is the range, magnitude of epsilon R and epsilon K. And the way we do it is by doing something called as sensitivity analysis. In one of the later lectures, when we will be looking at MATLAB, I will show you how to do sensitivity analysis in MATLAB. So, in sensitivity analysis what we do is when we have our model, we have put our parameters in, we have our data, and then we take one parameter at a time. So, we take R and then we vary R. So, we vary R and we look that when R changes, so del R by R, so what relative change I am making in the value of R, and what error epsilon R, or what change I am looking at the final result n. So, basically del n by n when I am changing R slightly by del R. This is sensitivity analysis, and once you do that on MATLAB or on R or any other platform, you will get information that can be plotted like we are doing it in this particular graph. So, if you look at this graph carefully, on x axis we have a list of parameters that went into the model for antibiotic resistance and antibiotics in the slurry tank in UK dairy farms. On y axis we have relative sensitivity. Now, zero sensitivity means I might vary the parameter, I might have a big error even in the value of parameter, but since the sensitivity is 0, I do not expect it to make any significant impact on the overall predictions. So, we see some parameters here like the transfer rate of susceptibility, susceptible bacteria, then there is alpha S. We see some parameters here who have nearly 0, like MIC of the bacteriostatic antibiotic, nearly 0 sensitivity. So, I do not need to be very exact about the value of these parameters. So, even if I am way off, let us say the value of this is, let us say R, let us say I do sensitivity analysis and I see for my logistic equation R does not have very high relative sensitivity, it is nearly 0. Then I know that it does not matter what value of R I picked up, it is not going to make a big substantial difference in my predictions. But then we look at other parameters such as alpha U, which is the cost of multi-drug resistance in the bacteria. And then we have theta L, which is the inflow rate of bacteriolytic antibiotic. L is for bacteriolytic, S is for bacteriostatic. These have quite an impact. Also alpha L, which is the cost of bacteriolytic antibiotic. So, sensitivity analysis tells me which parameters I need to be as exact as possible, and in case I am not, so if I know what error rate I am expecting, del R over R, what relative error I am expecting in my given parameter, in this case let us say alpha U, so del alpha U by alpha U, and then I can say alright, if I am expecting this range of error in my parameter alpha U, then I should expect this range of error in my predictions. So, this is very important analysis, and I'll show you with a very simple example how to conduct sensitivity analysis using MATLAB. Okay. So, a follow up of sensitivity analysis is the question I have been telling you, how do my results vary when the parameters vary. This graph tells me the sensitivity of each parameter. This graph tells me how the results are going to vary. So, on y-axis here we have the levels of multi-drug resistant bacteria RU, the kind of bacteria we are very concerned about. So, as you vary these parameters, you see it does not really impact the levels of MDR, multi-drug resistant bacteria, in your slurry tank. So, these parameters, then I know, are not going to have major impact. But then there are other parameters that are going to drastically change the results that I get if there is an error. This sensitivity analysis can also inform me, these are the parameters that we see will have impact. We can also see here what level of impact we are expecting, right. For example, alpha U, which is, as we looked here, the relative cost of multi-drug resistance. As we vary, as we increase the cost of multi-drug resistant to bacteria, we can see up to 10 to power 9 orders of magnitude. Remember, this is logarithmic scale, the y-axis. We can see 10 to power 9 orders of magnitude of difference in RU, which is the quantity of multi-drug resistant bacteria. So, we need to be very careful about our estimation of alpha U, and we can also say that interventions that change alpha U, that increase alpha U, can have very dramatic impacts on total level of antibiotic resistant bacteria. Okay. Now, this is also sensitivity analysis when we are doing seasonal emptying. So, you can do sensitivity analysis under different conditions, and we see when seasonal emptying is being carried out, then these are the parameters that are going to have significant impact if they are not properly estimated, or these are the parameters that we can vary to have significant impact. Okay. So, these are the heat maps from the result section of the paper, and what we are doing here is, it is again a follow up of the sensitivity analysis. On x axis we are varying the inflow rate of bacteriolytic antibiotic AL, and on y axis we are varying the cost of having antibiotic resistance towards bacteriolytic antibiotic and MDR, multi-drug resistance, so resistance to both bacteriostatic and bacteriolytic antibiotics on y-axis. And this tells me, the color here is telling me the proportion of MDR in the tank. So, I can consult these heat maps and also understand how things will change if I am able to stop, the inflow or change the inflow of bacteriolytic antibiotics in the slurry tank. So, for example, if I am able, because we noticed that bacteriostatic antibiotic inflow rate does not have much effect on the, does not have very high sensitivity both for no emptying and for emptying. We also noticed that if we vary theta S, it will not have significant impact on the on the levels of multi-drug resistant antibiotic. However, if we vary theta L, it does have an impact. So the second intervention so remember, the first intervention was changing the emptying interval, which we saw here. The second intervention is then stopping or changing the inflow rate of AL, which is bacteriolytic, and then we can consult these heat maps to estimate what ratio of change we are noticing. For example, if I know that alpha L is this much, right, and then I can see how if I vary theta L from small levels to higher levels, how the RU proportion will change. Okay, so these are some of the more results. Here we are looking at the multi-drug resistant proportion in tank after 20 years, so after a long time, when we are varying theta L and theta S. So and notice here, varying theta L makes a big impact, but varying theta S seems to have no impact, which is what our sensitivity analysis suggested. So this is when we are not emptying. So this is no emptying, and here we are emptying. What take home message I want you to know from these slides is you can look at your sensitivity analyses, you can estimate using that how the result, the endpoint that you are interested in, that variable will change as your parameters change, and then you can use that to design regulations which is clear from the heat maps. How much do I vary factor A, factor B, and can I mix the factors? So when I don't have seasonal emptying, when I have seasonal emptying, how can I mix these, how can I change these parameters to reduce or to attenuate the environmental problem that we are looking at. So students, as a revision, remember we took 3 lectures to discuss this paper, 2 lectures to build up the model to understand the problem, environmental problem, and then the 3rd lecture here was to give you an example of the kind of solutions or the kind of answers you will get using just empirical approach, using the parameter values that you get from the literature. I recommend you do read this paper if possible, and that will help you understand how useful in all the modeling studies that you have done so far can be to solve environmental problems. Later in the course, I will also be giving you example of how we can use the empirical approach to understand our anthropogenic activities contribution to global warming. Now, global warming models are very complicated. They require super high power supercomputers to run and facilities that we definitely don't have here within this course. Empirical approach in this case can be a refresher because we can use very simple models to get an overall idea of how things are changing in the environment because of human activities. All right, students, this is all for today. See you in the next lecture. Thank you.